If 10 people talk at once, your brain struggles to separate the voices. But a radio can hear hundreds of signals in the air and lock onto just one station. How does it do that? That ability to lock in isn't magic, it's physics. In this video, we'll see how an LCR circuit uses resonance to tune into a specific channel, and why some radios select stations more cleanly than others. The key idea is resonance. An LCR circuit has a special frequency called the resonant frequency, where it responds the strongest. That resonant frequency depends on the inductor and capacitor. Instead of watching the circuit wiggle in an animation, we can understand it with a graph: current versus frequency. At a very low frequency, the current is small. At a very high frequency, the current is also small. But for a fixed input voltage, the impedance is smallest at resonance, so the current reaches a maximum. So the graph tells a simple story. The circuit likes one frequency most, and it responds less and less as you move away from that frequency. Now, radio stations work by broadcasting at different carrier frequencies. For example, one station might broadcast at 101.1 MHz and another at 88.5 MHz. Your antenna doesn't choose. It picks up all nearby stations at once, so the electrical signal sent into the radio contains multiple frequencies mixed together. But the tuned LCR circuit does choose. If the resonant frequency is set to 101.1 MHz, the circuit produces a large current for that station, while producing a much smaller current for other stations. That stronger, on-frequency signal continues through the radio's detector and amplifier, so you mainly hear station A. The off-frequency station is much weaker at this stage, so it doesn't noticeably affect the output. To switch stations, the radio needs to shift the resonant frequency. A common way is by changing the capacitance using a variable capacitor connected to the tuning knob. Here's the relationship. If capacitance increases, the resonant frequency decreases. If capacitance decreases, the resonant frequency increases. So turning the knob literally slides the peak of the response curve along the frequency axis until it lines up with the station you want. Once the peak lines up with 88.5 MHz, station B produces the strongest current, so that's the station you mainly hear. So far, we have learned that resonance yields a peak response at one frequency, and tuning shifts where that peak sits. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. Now let's make it more interesting. Imagine two tuned circuits with the same inductor and capacitor, so they have the same resonant frequency, but different effective resistance that represents loss. The lower loss circuit has a sharp, tall peak. The higher loss circuit has a flatter, wider peak. Both peak at the same frequency, but their selectivity is very different. With a wide, flat curve, nearby stations can still create a moderate current. That means you may hear a little bit of an unwanted station mixed in, especially if the frequencies are close. With a sharp curve, the off-frequency response drops fast, so the radio cleanly rejects stations that are not right on resonance. Engineers describe this with a quality factor Q. High Q means a narrow peak and strong selectivity. Low Q means a wider peak, so more nearby frequencies sneak through. In this loss model, increasing the effective resistance lowers Q and widens the response. Lower losses raise Q and sharpen the peak, which improves selectivity. Let's practice. Suppose you're currently tuned to 101.1 MHz, but you want 95.9. Should the resonant peak move left or right? 95.9 is lower, so the peak must move left. That means you increase the capacitance, which lowers the resonant frequency. Here's the tricky part. When two stations are very close together, a low-quality, wide response curve may not separate them well, so you can get overlap. One common misconception is that the antenna is not doing the filtering. The antenna mostly collects signals. The tuned circuit inside the radio is what strongly favors one frequency. So the radio isn't decoding every station and choosing later. It uses resonance up front to favor one frequency far more than the others, while suppressing the rest. To recap, resonance makes an LCR circuit respond most at one special frequency. Tuning shifts that resonant frequency, often by changing capacitance, and the sharper the peak, the better the radio rejects nearby stations. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.